We're going to look at fundamental forces and their properties. Now we know about gravity. Gravity affects masses, but is only noticeable with very large masses. It's always attractive. For example, we feel the force of the gravity of the Earth because the Earth is so big and it's a force of attraction. Also, it's a dominant force over long distances. The distances between planets and so on is not felt by any force other than gravity. It also drops with the square of the distance. It is actually relatively weak, but as I say, works well over very large distances. On a small scale, on an atomic scale, because the masses are so small, it's actually really negligible. It's the force that keeps planets in orbits and stars in orbits and galaxies together and galactic clusters together too. The force is carried by a particle, a gauge boson called the graviton, which is massless and has not yet been observed. The electromagnetic force. Now we know about this. This also drops with the square of the distance. It is relatively strong. It's 10 to the 35 times greater than gravity. It also works over an infinite distance, but it only works if there's an imbalance of charge. If the charges are neutral, then there's no effect. It's a force that's responsible for holding atoms and molecules together. For example, the electron here is bound to the nucleus because of the opposite charges and the electromagnetic force. It can be attractive and repulsive. It's also responsible for magnetic fields, and it's carried by a particle called the photon, which has no mass. Now this is a nucleus, and by rights, because we have all this positive charge, the nucleus should explode, but it doesn't. So there must be another force keeping it together. This is called the strong force, or the strong nuclear force, and it basically binds the nucleus. So these forces, this strong nuclear force, is keeping the nucleus together. If you notice, the electrostatic force is repelling these particles, but there's another force, which is this strong nuclear force, which is actually considerably bigger at very small distances. At large distances it's completely ineffective. At very, very small distances it becomes repulsive as well. So this force only affects protons, neutrons, hadrons, which are heavy particles, and quarks. It's also very strong. It's 10 to the 37 times as strong as gravity. But it has a very limited range. It only works up to about 10 to the negative 15 meters. It's an attractive force, but with very small distances it becomes repulsive. And it's carried by gluons. Then there's a weak nuclear force, which is responsible for radioactive decay. Here's an example. We have an up, down, down neutron, which turns into proton because this down turns into an up, and it's mediated by a W, which is a boson, which basically causes an electron and an antineutrino to be produced. This is the force mediator, the W boson. The weak nuclear affects all particles, is responsible for radioactive and, or rather, beta decay. It's also responsible for nuclear fusion. It's weaker than the strong force, but it's and the electromagnetic force, but it's still 10 to the 24 times as strong as gravity. It has a very limited range, around 10 to the negative 18 meters, and it's carried by W and Z bosons, which have mass. That's why it has a limited range. Now the grand unified theory. Over 100 years ago, there were two forces, electrostatic and magnetic forces, which were considered as different forces. Then Maxwell basically understood them to be different aspects of the same fundamental force. So he said that this is not electrostatic and magnetic. It was one unified force called the electromagnetic force. Now it's understood that at very high temperatures, the electromagnetic, the weak, can combine to make the electro-weak force, and at higher temperatures, higher energies, with the strong and the gravity, it's possible that they could be fused to make all different aspects of the same force. And this is called the ground unified theory, that all forces are basically different aspects of the same force, but it only happens at super high energies, such as the Big Bang. And this may give us the answer to some questions. How did the Big Bang happen, and more importantly, why did it happen? How do forces work? They're basically transmitted by these gauge bosons, or the word is mediated by gauge bosons. These particles, these bosons, are virtual, which means they cannot be detected. And it works like this. You have these two particles, the person in the boat here and the person in the boat here. They exchange a gauge boson, in this case a large ball, and that exerts a force between them. This is an analogy of the way it works. They exchange this boson, and therefore they experience a force. This is a summary of the fundamental forces, and there you have it.